about the further optimizations, and that's something that pops up several times, which is the shared memory bank conflicts. So remember, our shared memory is this additional piece of memory that we have available within the streaming multiprocessor that acts between our threads, or that is accessible to the threads within a thread block and is shared across them. It is actually part of the L1 cache, so it's the same hardware as our L1 cache, and there is mechanisms of saying increasing the L1 cache at the cost or at the expense of a reduced shared memory. So in the Kepler architecture, these features are turned off by default, but if you're still working on the old Fermi architecture, that's one thing that you sometimes can play around and get slightly better performance. So if you know that you're not using any shared memory at all, you might want to increase the size of your L1 cache. You have not total freedom in choosing that. It's one thing where you have to basically 3 different configurations for the split between L1 and shared memory. Now, how is shared memory organized? Basically, this is now true for Kepler. It is organized in 32 independent memory banks. And that means a warp, which is 32 independent threads, can access independent banks for each one of the thread. So whenever you have a pattern like this, that each thread accesses a different bank, then you're perfectly fine. Then you get all the data that you need as quickly as it can get within a few clock ticks. There's a one-to-one pattern, and there is multicasting pattern. So if multiple threads access the same element in the same memory bank, then that's fine. There's no problem. However, you can run into problems when you have multiple threads accessing different values in the same memory bank. And let me see, I think I have more pictures here. So in the simplest case where you have the 32 threads, each one accessing a different bank, you're fine. Or in the other case where each thread accesses, again, a disjoint bank, you're perfectly fine. If you have multiple threads that try to access the same bank, you have a potential problem. What the hardware will do, I mean, just imagine on the electrical level, right? You have a wire between each one of the threads and these memory elements, and you're going and you're saying, hey, memory bank, give me this value at address A. And at the same time, you have another thread that says, hey, memory bank, give me this value at address B. Well, the memory bank can only give you one value at a time, because there's only one wire between the memory and the threads. So what will happen is that it's being serialized. So thread 0 will say, give me value A. At the same time, thread 28 says, give me value B. Value A will be delivered first, and in the second iteration, you will get value B. So that's the whole point of the shared memory bank conflicts, is that you're running into a problem when you have multiple threads accessing the same memory bank, and it cannot take advantage of the multicasting capabilities. So if thread 0 and thread 28 access the same value in bank 0, well, then it's being multicasted to those guys, and you, again, have no problem. And what the hardware will do is it will replay this instruction. So, as I said, it will first deliver the values to the first set of threads, then to the next set, and so on. So all this means is that you're just getting a slightly extra cost for accessing shared memory. Now remember our matrix transpose example that we had yesterday, right? What we said is we load our data from up there, into shared memory, and then we transpose it and write it back out. So I think, let's see. Okay, I have an example, a colored example here. Right, assume that we have bank number 0 to bank number 31, and in one case, we're loading the first, or we're writing the first column in shared memory. Well, we're ending up that all the threads, hold on, wait, we're writing a row. So in this case, all the threads are writing to the same memory bank. That means we have a 32-way collision or a 32-way bank conflict on bank 0, which is bad, right? Because this means your instruction will take roughly 32 times as long to complete as compared to the others. In the other case, well, access along row produces zero bank conflict. Well, it's now a question of how you interpret it. In one way, you're getting the 32-way bank conflict. I would actually claim in this, if we have, the labeling means green is bank 0, and red is bank 1, and blue is bank 31. So yes, in this case, we're accessing 32 different banks, no conflict at all. In this case, we have 32 threads accessing the same memory bank. That's maximum conflict. So the way to avoid that in case of a transpose is by not having a square of 32 elements. So by padding, instead of making our shared memory array 32 by 32 elements, making it 32 by 33 elements, we introduce a padding element. And so that means thread number 0 will go to bank 0, and then we have here a wasted element in shared memory. We're just not going to use that. But then thread number, on the next row, thread number 0 will write to memory bank number 1. Okay? So now when you're reading along, or when you're writing along the rows, well, you're touching 32 different banks. And when you're touching, when you're writing along the columns, again, you're touching 32 different banks. So this is a very simple trick where you're wasting a little bit of memory, but you're avoiding that you're getting this aliasing of your addresses when accessing when accessing shared memory. Yeah, I mean that's the key. That's one of the key optimizations there. Well, again, you basically reduce the cost of writing or reading by a factor of 32.
So the cost of that is you use more of the shared memory?
You're using more shared memory. Yeah, you're using this extra column of shared memory. But the benefit is that in this particular case, where you access across the column and everybody hits the same memory bank, this time the hardware has to issue first an instruction for thread number 1, then an instruction for thread number 2, for thread number 3. It is always a separate memory, a memory fetch. And yeah, that just takes a lot of time. And so removing this can speed you up quite a bit. Again, it's one of those optimizations that probably I wouldn't immediately spend a whole lot of time on it. The profiler will also tell you that you might have a shared memory bank conflicts. It can actually tell you how many when you run the application. So it's something that you don't need to do some tea leaf reading or anything like that. You can just base your assessment on these numbers and you see, oh, I actually have a huge amount of shared memory bank conflicts. Maybe I should do something about it. And the resolution in most cases is just something similar to this. So you want to make sure that no matter how you access, or for the access patterns that you need in your code, the shared memory access patterns, that you're making sure that you have disjoint memory banks that you're accessing. And So the banks are organized in words, so in floating points, 4 bytes. I mentioned this is not relevant for Kepler. So just one caveat, that is, right, we added more shared memory that we use by this kernel. And so if you're doing this excessively, well, it can hurt your occupancy because your one thread block uses too much shared memory, more than the 3K shared memory that you could use safely. And so, yeah, it could be that you're limiting your occupancy, and that impact might even be bigger. So keep an eye out for the occupancy when you start padding your shared memory arrays. And the other thing I wanted to mention is a little bit about control flow and instruction. And I know everybody's getting tired, so am I. Let's just jump to that. There was a question about what happens with diverging control flow, right? What happens when you have an if in your code? So, for instance, here we have our control flow, and we hit an if, and so there is a then clause, and then there is an else clause for colors in green. So now that we're not having a single instruction, but rather an entire warp of threads that execute in lockstep, well, these 32 threads will process, and then they hit the if, and so they go through the true branch. And let's assume all of the 32 threads have the same, evaluate the if in the same form. Well, then they just go through the true branch and then continue afterwards. The same if it's the else branch. Again, there is no extra penalty. You have to do this work, so it's just going to cost you the length of the green arrow. However, if you have the situation that a fraction of your threads goes through the true branch and a fraction of your threads goes through the false branch, well, you're being hit by the cost of both the true and the false part. So as you can see here, you now suddenly have much longer for this operation. So what you learn from this is that it's not fundamentally wrong to have conditionals in your code, but you want to make sure that at the warp level, 32 threads, that they make the same decision whenever you come to a conditional. And it doesn't need to be absolutely the same decision, right? It's just, if you have a chance of ordering your threads in such a way that you have a high likelihood that they will do the same decision, you're going to be less likely hurt by the cost of both the true and the false part.
How can you discuss that? Because this image that I would get an intuition that it's only as much cost as executing both of these.
Exactly. Yeah, exactly.
So for instance, in the case where you have like if without an else, then I get no hurt for the
Exactly.
time that dealt with.
Yeah, that is true. Yeah, I mean, so that would just be a predicated execution. If you have something like, whatever, if my element is smaller than 5, then I'm setting, or
Control divergence, for instance, for a check if we're not out of array index.
right,
Happens with this front position, for instance.
yeah,
Then there is no cost.
that there is not really a cost associated there. Exactly. Yeah, it's only, right, imagine if you had a situation like this, if you have in your code a huge switch statement, and you have 32 different entries, and each one of the switch entries is a large piece of code. In that case, in the worst case where each one of the threads makes a different decision, well, you're going to be hit by all 32, by the latency of all 32 different paths through this switch case. So that's kind of the worst case scenario. But again, that's long story short. Just try to group your threads in a way that you probably want to make them go the same route. Yes. Exactly. Yeah, I mean, they will be like in this example, right? Here we have 3 that go through the true branch and 3 that go through the false. Even if this would be 30 that go through the true branch and just 1 that goes through the false, well, the 30 here will be carried through the false branch they're just idling. They can't do anything. And again, keep in mind you're issuing instructions that just go for 32 elements at a time. And the only way that you can mimic this independent behavior that we present you with CUDA, where you're saying I can do whatever I want with my single thread. The only way to give you that is by predicating out all the other threads, by just making them idle while you're doing your own stuff. So, yeah, I mean, we're not really advocating this this approach, but right, you could, for instance, have a kernel where you have something like, if my TID modulo 2 is 0, then I'm doing A equals my array of TID, else I'm doing whatever, my A of TID is 42, okay? So every second thread does something else. Basically, I'm having thread number 0 loads A, thread number 1 writes out, thread number 0 loads, thread number 1 thread writes out, and so on. This is not a particularly good pattern, because it will mean that you're just going through, every single warp goes through both the true and the false part. Because, yeah, what will happen is that up here, every second thread will be masked, and then it will go to the next, the false, and will be masking all the other threads. So rather than doing this, you probably want to have TID less than whatever. Just pick a number. My TID less than 64, make the load, and else you're writing out. Not to mention that the modulo here, even though this will be replaced with a shift, but if you had some funny business, at that point, this would actually be a relatively expensive operation, and you, yeah, this wouldn't be performing very well. So you rather want to just group the guys together who do the same route, and then have the other threads go the other path. And yeah, that was just a question of whether you have a power function or whatnot. The runtime library, math.h, has actually all these, pretty much anything you need. There is still the rumor that GPUs are not as accurate as other devices. This is not true. We have full IEEE 758 standard for floating point operations, and also these functions implement the transcendentals at full accuracy. But we also have hardware support for some of the commonly used operations, which are operating at a lower accuracy. So we have an intrinsic for the sign, for instance, that runs at lower accuracy, but is hardware supported. Yes?
In a kernel, I don't use these, but by mistake I use the GPU version, basically what happens.
Yeah, so if you're using, within the kernel, if you're just saying sign X, right? This means that you're using the IEEE compliant form on the GPU. Okay, so this gives you the correct answer. But the way that we're doing a sign computation, for instance, especially in double precision, is that we use the hardware function as an initial guess, and then we do a bunch of Newton iterations to get to the accurate result. So it's fairly expensive. However, if you say, I don't care, I'm perfectly happy with a slightly wrong answer, you can directly call the accurate forms, the hardware instruction for sine. And in this case, this translates into a single instruction and is much, much faster. So it's all, this is all nicely documented in the programming guide. So just have a look there if you care about accuracy. There is actually a way of just keeping everything in your code as sine, and so with basically writing it in the full accuracy. So calling just sine of x. That means if you're not doing anything and just compile it with NVCC, you will get the slower but correct answer. And then you can throw a flag. Is the flag labeled here somewhere? No. Let's see. Nope. There's a flag, use fast math for NVCC. And what it will do is that all the calls to the transcendentals, to any of the other functions in math.h will be replaced with their hardware equivalent. So instead of using sine, it will then use the underscore sine f. That translates into a single instruction. It's going to be slightly inaccurate. Again, we're talking about the last bits of the mantissa. It's not a huge error that you're introducing, but it has a slightly different rounding, for instance. So yeah, that's a quick way of turning those on. Instead of modifying the code, just use --fast math. Okay, and I guess we leave it there.